Today we're going to be talking about the frequency response of our amplifier. So to kick things off, we are going to do a very basic review of transistor amplifier frequency response. And really just kind of hit the highlights of what we need to understand how to analyze our particular circuit, the single stage op amp. So I'm going to start with a graph. Here we have our voltage gain, decibels. And then here we have our frequency measured in hertz. And what we learned in 336 is that our frequency response curve should look something like this. This is just a break in our curve to cover a large range of frequencies. So, and for me. This region here from where our voltage gain is at its peak and up to 3 decibels lower than that is largely the important bit here, okay? So we are going to call this region in the middle the midband. And what we learned in 336 stated effectively that in the midband, our voltage gain has a constant value and all of our capacitors can effectively be neglected. So in the midband range of frequencies, all of our coupling capacitors that were used to bias our circuit look like short circuits, and all of our internal capacitances, junction capacitances and things like that that are inherent to our transistors look like open circuits. On the left-hand side, we have our low frequency band, where all of our coupling capacitors are transitioning from open circuits to short circuits. And over here on the right-hand side, we have our high frequency band, where all of our internal capacitances are transitioning from open circuits to short circuits, okay? So our bandwidth of our device ranges from F low, our first 3 decibel cutoff frequency, all the way up to F high, our second 3 decibel cutoff frequency, okay? So for an integrated circuit, the frequency response graph is going to look slightly different. And the reason why it's going to look slightly different is because we don't AC couple our input signal. Instead, we tend to DC couple our input signal. So this is for typically discrete transistor amplifiers. For integrated circuits, it'll look something like this. Effectively, the low frequency roll off is non-existent because we don't have any coupling capacitors influencing our frequency response. We have mid-band all the way up to that corner frequency, at which point we hit our high frequency band. This is F high. This range is 3 decibels. So this is for IC amplifiers, okay? So the bandwidth of an integrated circuit amplifier effectively extends all the way from DC up until we hit that corner frequency. So when we are designing an amplifier, it is typically speaking our goal to maximize both the gain of our circuit, the voltage gain AV, and the bandwidth of our circuit in our design. So effectively, we are designing towards the highest gain bandwidth product that we can achieve, where GBP is simply AV times omega high, using the angular frequency location of the pole as opposed to the linear frequency location of the pole. They're effectively the same thing, okay? So this is the quantity that we are going to use as a figure of merit. All right, so now let's talk briefly about poles, zeros in our frequency response plot. So if I have a Bode plot, in hertz, like so. So if I have a Bode plot for an integrated circuit, it might look something like this. Where in this region, my slope is negative 20 decibels per decade. In this region, my slope is negative 40 decibels per decade. And in this region, my slope is once again negative 20 decibels per decade. These break frequencies, where we see a change in the frequency response, are indicative of either poles or zeros in our system's transfer function, where a pole frequency corresponds to a corner or break frequency at which the slope of the magnitude curve decreases at a rate of 20 decibels per decade. So if we look at our graph here, Our voltage gain is a constant value until we hit this first break or corner frequency. And then we see that our slope has changed from 0 decibels per decade to minus 20 decibels per decade, which indicates that there was a pole in our transfer function at this location. Similarly, as we get to our second corner frequency, we see a subsequent increase in our slope of an additional negative 20 decibels per decade, which indicates that we have hit a second pole in our frequency response. A 0 frequency corresponds, to a corner frequency at which the slope of the magnitude curve increases. At a rate of 20 decibels per decade. So if we look at our third corner frequency, since our slope changed from negative 40 to negative 20, we have an increase in the slope of 20 decibels per decade, which means this frequency here corresponds to a 0 location. All right. And we can also determine poles and zeros from our amplifier's frequency response, right? So in general, the frequency response of our system as a function of S will be of the form A midband. So this is our midband gain multiplied by a ratio, 1 plus S omega Z1 times 1 plus S omega Z2 all the way to 1 plus S omega Z to the N. All of this divided by 1 plus S omega P1, 1 plus S omega P2 to 1 plus S omega P sub N. So effectively, if we can get our transfer function, this is just the ratio of our output voltage to our input voltage as a function of frequency. So if we can get our transfer function in the form that we have the midband gain, which is what we've been calculating up to this point, multiplied by a ratio of polynomials, any 0 in the numerator polynomial corresponds to a 0 frequency, and any 0 that we get in the denominator corresponds to a pole frequency. So as designers, we are principally concerned with the location of our first corner frequency. So largely, we're only concerned with this guy. You don't necessarily have to change your color unless you want to, Stephen.
I gotta use it.
Yep, okay. So the reason why I say that this is the frequency that we're principally interested in is because this is the frequency that tells us what our bandwidth is. Everything beyond this point, our gain is no longer at its maximum value. And so we, generally speaking, don't particularly care how the amplifier behaves beyond this point. Now that's not wholly true. And we'll talk about when that's not true when we talk about compensation and all that kind of stuff later on this week. But for the most part, at least for today, This is what our principal concern is, figuring out how to figure out what this first corner frequency is. So in order to simplify the analysis that we are going to be doing, we are going to use Miller's theorem so that we don't spend 3 class periods doing algebra. We just spend 1.
Flashback to circuits 3.
Yeah. So let's talk about Miller's theorem revisited. And if at any point you want me to slow down, tell me to slow down. All right, so Miller's theorem, I'm going to write this out. You guys don't necessarily have to. Miller's theorem states that if an impedance Z is connected between the input and output terminals of an amplifier with gain A the impedance Z can be replaced with 2 impedances. Z1, which is placed between the input and ground, and Z2, which is placed between the output and ground. So graphically, if we have the following situation, I have some input signal X, do not particularly care if it is a voltage waveform or a current waveform. That is, serves as the input of some amplifier A. And then over here, Y is equal to A times X, right? So here's a simple amplifier. If I have some impedance Z that is effectively a feedback path between my input terminal and my output terminal, Miller's theorem allows me to refer some portion of Z to the input and some portion of Z to the output. Today, we are going to be dealing with feedback capacitance. So for capacitive impedances, we know that the impedance of our capacitor is by definition 1 over j omega c. And using the rules for Miller's theorem, what we'll find is that the impedance Z1 will be our feedback capacitor's impedance Z divided by a factor of 1 minus A, which is our open loop gain for that stage of our amplifier, which in turn tells us what capacitance is referred to the input side. In this case, it's going to be 1 minus A times our feedback capacitance C. Okay, so I want to point a couple of things out here. Our amplifier that we are dealing with, our differential pair, is effectively based off of common source amplifiers, which have a large-ish negative voltage gain. So effectively, any capacitance that we have in a feedback thing is going to wind up making a larger capacitance appear at the input. Now, let's look at the output side. Impedance Z2 is given by Z divided by 1 minus 1 over A. And so our capacitance at the output, C2, is going to look like 1 minus 1 over A times C. So if our voltage gain is large, this is approximately C. Or A much greater than 1. So the impedance that's referred to the output, or the capacitance that's referred to the output terminal, is effectively going to be very close to what the feedback capacitor was. So that's a reasonable estimation. All right, so now we're going to look at our frequency response of our single stage op amp. So our single stage op amp circuit, which I'm sure you guys know what this looks like, but I'm going to draw it for a specific purpose here. Looks something like this. Here's VN1, transistor M1, this is M3. Here's M2, 4, VN2. Here is our tail current, ISS. So what's interesting slash kind of annoying about this particular circuit is that it is asymmetrical, which means we can't use the half circuit to determine its frequency response. It would, if it were symmetrical, we could just look at the frequency response of a common source amplifier, which is pretty well behaved. Another thing that's interesting is because we have a differential input and a single-ended output, we effectively have two signal paths to worry about. So we have an input signal from VN1 and its signal path to the output. And then we have our signal path from VN2 to the output, both having separate transfer functions that we effectively add together. So to make our life mildly less miserable, we are going to approach this by effectively splitting things up to some extent, okay? So I'm going to call this node X, and I'm going to call our output node Y, and we are going to associate resistances and capacitances with each of those nodes in order to facilitate figuring out what our transfer function is. So effectively, why this works or why this is a good approximation goes back to what we did last Wednesday, I believe, when we looked at the small signal analysis of this particular amplifier, right? So the diode connected resistor, or excuse me, the diode connected transistor M3 is going to contribute some resistance that's seen by our input signal VN1 that in turn influences the voltage that appears at node X. Because the voltage that appears at node X controls the amount of current that is being sourced by M4, that effectively characterizes that topmost signal path. And then we just look at the bottom signal path from VN2, and we're effectively done, okay? So let's start by looking at the resistances. And to do this, we are going to look at our small signal model. So determining Rx and Ry. So our small signal model, let's start here. So here is, nope, I'm going to move this lower so that I'm sure I have enough room. Sorry. Here's the gate of 1. Here's VGS1. GM, VGS1 in parallel R01. Up here, I'm going to put transistor M3's small signal model. So here's GM3, VSG3 in parallel with R03. This is my source of 3. This is my source of 1. This is my drain of 1. Here is my drain of 3. Plus minus VSG3. My drains of M1 and M3 are tied together, and I know that my drain of 3 is tied to the gate of 3, like so. Now I'm going to work on the right-hand side here. Here's R02 in parallel with my current source, GM2, VGS2. This is my drain of 2. Since I'm looking for resistance, I'm going to short my input node. This is the source of 2 and the gate of 2. Up here, I'm going to draw what's going on with transistor M4. So this is GM4, VSG4 in parallel with R04. We're source of 4, drain of 4, plus minus VSG 4. Here's my output node. I know that the source of 1 and the source of 2 should be tied together. And because this is very close to symmetrical, once again, we are going to deal with an assumption here that this node down here at the bottom is very close to ground. Okay. So this is, what color did I use? Node X. This is node Y. So what resistances do we see associated with node X? So between X and ground, we have R01 for sure. Between X and ground, we also have R03. And because of our diode connection, there's a linear relationship between the voltage drop across our current source here and the current flowing through our current source. So this current source effectively behaves as a resistance. 1, my stylus will write, over GM3. Which will look approximately like 1 over GM3, since R01 and R03 should be orders of magnitude larger than 1 over GM3. Anybody have any questions, comments, or concerns here?
So if you didn't ground that common node, solve the slight effect of G1.
So since we're looking for resistances specifically, we have our input terminals effectively shorted out, which means that GM1, the current source GM1, VGS1, is going to behave like an open circuit in this particular calculation. Like if we put a test source between here and ground, it would more so look like R01 is a dangling thing. Now, in truth, what we would actually see would be the internal resistance of our tail current source being degenerated by there. And that's just going to make the math harder. It's also going to make R01 look even larger because that's what degeneration does, which is not going to change the results of our analysis. All right, now let's look at RY. So what resistance do we see between node Y and ground? So there is no linear relationship between VSG4 and the current that's flowing through that GM4 VSG4 current source. So that doesn't look like a resistance. We see only R02 in parallel with R04. So those are our two resistances. Are we okay with that? Is anybody willing to say they're not okay, I guess is a better question. All right. So now let's look at our capacitances. So I'm going to redraw our circuit. So let's see. Determining CX and CY. And we're going to do this one a little more so by inspection. Okay. So I'm redrawing my circuit, giving myself enough room to do some things here. Bless you. All right, so this is M3, M4, M1, and M2. And now we're going to be identifying and putting in our high frequency capacitances, which I'm going to do in this purple color. So let's start with transistor M1. We're going to have some gate source capacitance, CGS1. We are going to have a gate drain capacitance, CGD1. We are going to have a drain body capacitance, CDB1, like so. Similarly, for transistor M2, we will have all of those capacitances. So CDB2, CGS2, CGD2. Now let's work on M3. So between our gate and ground, you're going to have this guy, CGS3. We are not going to have one between our gate and drain because it's shorted out by that diode connection. So here's CDB3. Now we deal with transistor M4. So here we have CGS4, CGD4, and CDB4. So let's start with CX. We're looking for capacitances between CX and ground, where here is X and here is Y. So let's start with the obvious ones. CDB1 is obviously between node X and ground. CDB3 is obviously between node X and ground. CGS3 is obviously between the X and ground. And CGS4 is obviously between Bx and ground. Okay, but there's one more capacitor that we need to consider here, CGD1. So CGD1 is a feedback capacitor between the input of M1, the gate, and the output of M1, the drain. By using Miller's theorem and treating this small stage as effectively a common source amplifier, we can refer CGD1 or some portion of CGD1 to the output. If our gain is large, effectively all of CGD1 will appear at or connected between the output and ground. So I'm going to put CGD1 here, and I'm going to put a little asterisk here that lets us know this is actually not, this is an approximation, because we are using Miller's theorem to approximate what that capacitance is going to look like between that node and ground. Are we okay with that? We're going to do a similar thing for CY. Okay. So between node Y and ground, we have CDB2, CDB4, CGD2. That'll be a Miller one, and CGD4. And I'm going to do something else here really quickly. I mentioned this the other day, that our single stage op amp is effectively only capable of driving capacitive loads. So let's consider what happens if we also have some capacitive load connected to our device. So I'm going to put plus CL here as well. We'll talk about why that's important in a few minutes. So I now know all of my capacitances, or what the equivalent capacitance connected at node X looks like, what the equivalent capacitance at node Y looks like. Okay, I know the equivalent resistance connected to node X. I know the equivalent resistance connected to node Y. So I'm going to put all of this information together. Can I go to the next page, Sam, or you? You good?
What's the CB? What was that last?
CL, the load capacitance.
Sorry, I was only on this.
Nope, not a problem. All right, we good now? Okay, so now that I know the resistance connected to node X, or between node X and ground, the resistance connected between node Y and ground, capacitance connected between node X and ground, and the capacitance connected between node Y and ground, I am going to draw a equivalent circuit here. So putting all of this information together, our circuit will look something like this. So here is GM1 multiplied by input differential mode voltage over 2. So effectively, we know that if VGS1 is VIDM over 2. In parallel with RX, in parallel with CX, and then this voltage is Vx. Over on the right-hand side here, and this is all going to share a common node at the bottom. Okay. I have current pointed up. That is going to be GM2 times positive VIDM over 2 in parallel with the current pointed down, which is GM4 times Vx. In parallel with that, I have RY in parallel with CY. And the potential difference here is my output voltage. Now I want to point out something really quickly here. I'm going to scroll up. The current source direction of GM2 VGS2 is directed down, okay, in this drawing. In the drawing that we just did, its direction has been reversed. Its direction has been reversed to accommodate the fact that we are applying a negative voltage there, negative VIDM over 2. To get rid of the negative sign, we change the direction on the current source. Similarly, I change the direction on the current source GM4 VSG1, or excuse me, VSG4, because VSG4 is the same as negative Vx. So again, to get rid of those negative signs, I change the direction of those sources. So I just wanted to be very clear about why the directions are different than is indicated on my original diagram. Okay. So now we're going to develop our transfer function. So using Ohm's law, we could say that Vx is going to be negative GM1 times VIDM over 2, where the negative sign here is coming from the fact that the current is flowing into the negative polarity terminal. And then we have 1 over GM3, which is just Rx, in parallel with 1 over S CX. That's just Rx in parallel with the impedance of CX. Now, effectively, I have two admittances in parallel. So I can just lump them together. Admittances add directly. So this is going to look like negative GM1 times VIDM over 2 times 1 over GM3 plus S. Are we okay with my application of Ohm's law here? Voltage is equal to current times the equivalent impedance. All right. So now let's figure out the out. So I'm going to have a positive GM2 times VIDM over 2 minus GM4 VX multiplied by RY in parallel with 1 over S CY. Okay. We're going to expand this out here in just a moment, but I'm about to do some math here that I want to explain very briefly. So I'm going to jump ahead a page. You don't need to write this down. I just want you to show, I want to show you where this form is effectively coming from. So if I have a resistance in parallel with the impedance of a capacitance, this is R over SC divided by R plus 1 over SC. Multiplying through by SC over SC gives me R over 1 plus SRC. So I'm going to use that identity here to put things in a form that is less awful. Okay. So this is going to look like GM2 times VIDM over 2 times R02 in parallel with R04, which is just RY, over 1 plus S R02 in parallel with R04 times CY minus GM4 times R02 in parallel with R04 over 1 plus S R02 in parallel with R04 CY. So what I just did here, to be clear, is I took care of this part, and now I'm about to multiply through by Vx, just direct substitution there. Since Vx is negative, it's going to change that sign. I'm going to have GM1 times VIDM over 2 times 1 over GM3 plus S CX. And now I'm going to do a little bit of factoring. This, promise you, isn't going to be supremely horrible. So recognizing that GM1 and GM2 are the same quantity if transistors M1 and M2 are perfectly matched, I have a common factor of GM2. I have a common factor of VIDM over 2. And I have a common factor of R02 in parallel with R04 over 1 plus S R02 in parallel with R04 times CY. And so I'm just going to make some check marks here. So I've taken care of this guy, this guy, this guy, this guy, this guy, and this guy. All this multiplied by 1 plus GM4 over GM3 plus S CX. And now I'm going to rearrange things again very slightly here, just to get it in the form that we are expecting. Okay, so I'm going to pull my VIDM out in front. Then I have GM2 multiplied by R naught 2 in parallel with R naught 4. And I'm going to make a designation here. That's our mid-band gain that we came up with the other day. I have 1 over 2 times 1 plus S R naught 2 in parallel with R naught 4 times CY. And then now I'm going to deal with this 1 plus GM4 over GM3 plus SCX bit by treating 1 as GM3 plus SCX over GM3 plus SCX, giving me GM3 plus GM4 plus SCX all over GM3 plus SCX. My transfer function would then be V out divided by VIDM, which is just everything to the right of VIDM. So I have it in the form mid-band gain multiplied by polynomials in S. From this, I can see that I'm going to have a pole. Let's say omega P1 is going to be at GM3 over CX. I'm looking at the second half or the second polynomial in my transfer function here. I'm also going to get a 0 from this part. So omega Z1 is going to be GM3 plus GM4 over CX. And since GM3 and GM4 should be identical, we can just call this twice GM3 over CX. From the first part of my transfer function, I get a 0, or excuse me, a pole. Let's call that omega P2 is equal to 1 over R naught 2 in parallel with R naught 4 times CY. So which of these guys do you expect to be the dominant pole or occur at the lower frequency? Which resistors should be bigger? RX or RY? RY. R naught 2 in parallel with R naught 4 should be significantly larger than 1 over GM3. So this guy is effectively our dominant pole and sets our bandwidth. From this, our gain bandwidth product, GBP, is our mid-band voltage gain, GM2 multiplied by R naught 2 in parallel with R naught 4 multiplied by our bandwidth, 1 over R naught 2 in parallel with R naught 4 times CY. This bit cancels this bit, and it's literally just GM2 over CY. If we look at all those capacitances that make up CY, the largest one of those, and therefore the most dominant part of that expression, will very likely be our load capacitance, meaning how we load this thing contributes directly to our gain bandwidth product. The size of the capacitor that we use is going to limit the overall performance of our device, and that's going to lead us directly into frequency compensation, which we'll talk about on Wednesday. Sure. Or another way to think about frequency compensation is what happens if we include feedback? Because as we all know, op amps, generally speaking, are not operated in an open loop configuration, but instead, for amplification purposes, is usually in a negative feedback thing. So we are going to see how, with a capacitive load, a simple unity gain buffer makes this device unstable at present. So that's what we're going to talk about on Wednesday. All right, I'm done.